Okay, the maximum value of coefficient of variation. So the main focus of this study here is to analyze the maximum value of coefficient of variation for some statistical and data distribution in which we have. And then at the end of the study here, we will reach to a conclusion that the upper value of the coefficient of friction or coefficient of variation for a number of data, and this is then the new property of the data. Okay, the second point here. Now, if for example we come to properties and measures of data, usually in statistics, I think all of us we know the fact that if you have got data, in data you can measure or you can calculate something in which is called mean. Mean is a property of data. Each data may have a different mean or another mean, and then variance, skewness, and distribution of the data is also a property, and many more. Definitely here, there is no way in which we can display all of them here. And in practice, maybe there are infinite number of those properties. Some of them we know, and some of them we do not know. And then, in the same way as you have got a physical object, so if you look at physics, for instance, here, you do have similar that in chemistry or in any other science. If you have got an object, the object may possess something in which is called elasticity, maybe something like density, maybe something like viscosity, geometrical shape, and etc. So there is a quite similarity between the two. And again here in practice, maybe there are many, many more. And it depends on the purpose of your study. For what purpose, for example, you would like to study density, for what purpose you would like to study elasticity, and so on. And the same thing for data. For example, to some researchers, maybe distribution is interesting, to some maybe skewness, to some maybe variance. Okay. Now, comparison. Usually in practice, we know the fact in any research study or in any study here, if I'm talking about, let us say, physics, maybe some people are interested in whether the density of water is more or less than the oil. Comparison idea. So comparison idea is always there in any study. Modulus of elasticity of steel is more than copper. Always we comment on those and then we analyze those and more. In statistics, we do have a similar idea here. For example, here, maybe someone is studying the mean weight of Indian tigers. Is it bigger or is it smaller than the median weight of the African tigers here? Okay, this is a comparison between two means, and this is the conclusion of your research. The skewness of wealth distribution in two different countries. Are they significantly different or are they the same, and so on. Okay, so now the next job, there is an element in which I'm focusing definitely in this study here, because I cannot comment on all the possibilities or properties as we explained, is variation. So an interesting study usually in statistics is variation of data. Variation of data means how spread the points of the data are apart or very close to each other. If, for example, you have got some data in which the points are very close to each other, qualitatively we can say the variation is small, but if the points are very far away from each other, the variation is large. But definitely in statistics, we would like to introduce a quantitative measure. I have given now two examples here. One example is, imagine, for example, you have got a sample, just for simplicity here, 3 elements here. The measurements of weights of some people here in sample in college, then 60, 65, 70, and then if you calculate the mean is 65 kilograms, which is fairly easy, and if you calculate the standard deviation, which is 4.08 kilogram. But if, for example, in sample 2, and then you have taken, let us say, 3 elements here, the measurements are also in kilogram. If you work out the mean, you notice that the mean of this data is 65, which is the same as the other one. And certainly here, if you make a comparison between these two data on the base of mean, you may say, okay, the two data are the same. In the same way as you have got in physics, maybe 2 densities of 2 different materials are the same, but there is a difference in refraction, for instance here. While the standard deviation is different from that. Certainly here, the degree of the spread of the second data is more. And both of them have got units of kilogram. But now if you make a comparison between two other data, while one of them the unit is in kilogram, while the other unit is in centimeter, you will get two different impressions. Then there is no way in which you can say this is bigger than that or this is smaller than that. Because one of them is kilogram, one of them is centimeter. Then comparison between their standard deviation cannot be done here. You cannot make a comparison, or you cannot comment on a comparison between variation of these two distributions according to the principle or the base of standard deviation. That's why now we introduce a measure, and this measure we call it coefficient of variation. What is coefficient of variation? Simply is the definition is the dividing by of standard deviation divided by the mean of the data. And then in general, although this needs definitely a new study here or a new video to comment on those, but in general we can say we categorize into three groups. There are some groups of data in which the coefficient of variation is less than 1. There are some groups of data is 1. There are some groups of data in which is greater than 1. Although the main focus of the study, as we explained, is the upper limit of this coefficient of variation, regardless of that. I started it here with a simple raw data. Simple raw data is simple. It means you have got just a set of data in the way in which we have in reality measurements of x1, x2, x3, and so on. So it means just n elements of data. Imagine, for example, you take a sample of 10 students here, and then you measure the marks in which they got in a certain exam. Okay? Then this is mathematically the definition of variance or standard deviation here, which is the square of the variance, definition of mean here, and then after simplification here, then you get the structure. Now the idea here is how we reach to that conclusion that the upper limit in the case of raw data does not exceed the root of n minus 1. Let us assume, for example, any of those elements here, whichever element like xi is as large as possible, 1 million, 10 billion, trillion, and so on. So if you do your calculation, you can simply reach to a conclusion after some simple calculus, by the way, to that the coefficient of variation does not exceed that. So it means for raw data, the coefficient of variation cannot exceed the root of n minus 1. So the upper limit is n minus 1. If, for example, any element of the data approaches infinite. Okay, so this is going to be the upper limit here. And then demonstration of this is a simple mathematical proof, which is fairly very easy. A simple demonstration can be done easily here. If you bring a spreadsheet and then put some numbers, like here, for example, I put, let us say, 50 numbers here, and then any random numbers, by the way, and then make, let us say, your calculation here according to the coefficient of variation. You put your input formula, and then make any of those data, choose any one of them, put 10, then increase it to million, increase it to 10 billion, and you notice that there is no way in which the coefficient of variation will exceed this limit here. Because definitely you cannot have infinity in your computer. That's why maybe you don't get exactly 7. So it means always maybe is remaining at 6.99. There is a special case here of interest. So it means this special case here, if I have got the data, and the size of the data is n, and then if all of them are 0 except one element, whatever the value of k is any arbitrary constant here, and then you notice that you don't need to have k as infinity, and then the value of Cv, which is coefficient of variation, comes out to be exactly equal to the root of n minus 1. This is a quite interesting new result here. Okay. Now, the next job is if we extend the study here to continuous distribution. Continuous distribution, certainly I'm not commenting on the types of distribution, but I just take two examples here. One of them is uniform distribution. Uniform distribution is fairly easy. This is the shape of the probability distribution. this is the mean, this is the standard deviation. I don't need to derive those. The derivation, you can find it in many textbooks of statistics. My main interesting point is the definition of CV, and the definition of CV here is certainly the standard deviation divided by the mean, and then if you can simplify this in the same way as we had here, we reach to a different conclusion, but still the upper limit. So it means simply here, for the uniform distribution, the CV at the limit will approach 1 over root 3. Okay? So this is for the normal distribution. Now the next job is continuous distribution, the next type of continuous distribution, and this is the graph of CV against the value of B. B is the other value which you have here, and then certainly if you plot the function, and then you notice that this is like an asymptote, 1 over root 3, and then it does not exceed more than 1 over root 3, whatever the value. And this can be now a new property of uniform distribution. The next distribution is triangle or triangular distribution. This is a shape of triangular distribution in which you have the 3 parameters, alpha, beta, and c. This is a generic shape here. And then the mean of the distribution you can easily calculate from some simple calculus. And then the standard deviation can be this. And this is going to be the CV. And the CV is defined in the following way. And again, if you take the limit, if beta becomes very, very large, then you notice that in the case of triangular distribution, CV will become the maximum of 1 over root 2. And you can easily test it. Whatever the value of B in which you increase, or whatever the shape of this triangular distribution, there is no way in which the CV can exceed this amount here, which is 1 over root 2. And definitely for many other distribution, I will leave it for yourself to study further distribution, but this can be a new property of the data. Lastly, invariance of CV. What does it mean? It means if, for example, let us say we amplify the data by factor of S or factor of F or whatever, it means the standard deviation definitely changed, the mean also changed, but as the result, the coefficient of variation does not change. If, for example, I have got x1, x2, and 2xn, and then if I calculate, let us say, coefficient of variation, if I have got now x dash, x2 dash, and then xn dash, in which by definition, let us say x is equal to some factor times the original data, and then you have got c dash nu, and then you can easily demonstrate and show that CV and CV dash are the same. So it means it does not change. So the final conclusion of this study here is just adding a new property of the data, which is the upper limit of the value of the coefficient of variation. Okay, thank you for watching this clip here. Thank you. How long was it?